Hi everyone, it's Peps here. Welcome back to the channel and to another Houdini tutorial. Today we're going to create this kind of effect, which maybe resembles somewhat of a neural system, I don't know. But basically we will do everything from scratch with a Sop Solver. We will start with an initial set of points, and inside a Sop Solver we will create all the behavior with vex. So we will end up with something like this. So, as usual, let's start from an Houdini empty scene and let's create a geometry container. We'll call this neural and dive inside. And in here, let's drop down a sphere, so we will have some geometry to scatter the points on. Let's make it as a polygon type, increase the frequency, and for the time being, let's just make it with an uniform scale of 1, so we can see better the points and all the vector and attribute that we will create. So let's take a scatter node, and for the time being, let's just scatter, let's say, 4 points. And after the scatter, we want to use a point wrangle so we can initialize some attributes. So let's go to the point wrangle, let's call it init attrib. And for now, let's build only the main thing that we need to have to just start the system. So we will need a vector direction. So let's create a vector variable. We will call this dir. And for now, we will point it on the y-axis. So set 0, 1, 0. And let's create another one. This will be our up vector. So vector up, and we will point it on the z-axis. So set 0, 0, 1. Let's bind it to a couple of attributes. So v at dir is equal to dir, and v at up is equal to up. If we create the visualizer for it, so 1 and 2, and by default the up vector, it gets interpreted as a vector marker to visualize. Let's make it red. I'm more used to it. And we need to change the direction type because by default it gets read as a color marker. So let's change the type to marker and the style to vector. So now we have the points, and the points have a direction vector and an up vector. So we want to drop down a solver. Let's call it draw and dive inside. So inside the solver, let's create also the things as we need. So the first thing is to actually apply some modification to the position. So let's take a point wrangle. We want to plug it between the previous frame and the out. We will use always the previous frame as a source stream. And let's call this update position. We will have a few point wrangles, so it will be a good idea to name it so we can know where we are working. So in here, basically the tweak to the position will be just an addition. So at p plus or equal, we will use the direction vector we created, so v at dir, and that's it. If we go outside the solver and scrub the timeline, the points are actually moving. The movement, of course, is super fast because we are adding a whole unit each frame. So let's also create some step channel to control the speed. So float step, it will be equal to a float channel. So CHF, let's call it step. Click here to create the space parameter. Let's set it to 0.1, and we want to multiply the direction vector for the step variable. So now we slow down the particle. Problem is the speed is basically uniform for each point. So later on, we will also create some random value based on the point number because we will generate point as we go. But for now, let's compute some global speed value different for all the points outside the solver. And we want to do it before the scatter. So let's take a point bob. We will compute the speed value with a simple noise. Let's call it calc speed. And inside, let's just plug the position into anti-alias noise. It should be the lighter one. And this will be plugged to a bind export so we can create the speed attribute. If we go outside and visualize it, I already have the visualizer, we have something like this. So we want to do something less rough. So let's say 0.15, and let's crank up the amplitude a lot, something like 5. And let's go on the geometry spreadsheet. Let's see, we have something going from negative 1.2 to the positive. Let's take a fit range. And let's say we want to fit from negative 1.5 to 1.5. And we want a possible speed going from 0.5 to 1. So basically half the values. So now we have something going from, let's say, 0.5 to 1. And let's go outside. Let's make sure they are inheriting the speed attribute. And here we also have it. So if we go on the growth solver inside, let's multiply all of this, or rather multiply this step for the f at speed we just created. So let's play it, and we should have different velocities on the points. So we still have the vector all pointing up. We will change that, but for now the idea to modify the direction over time is basically we will create two oscillator, let's call it this way, with a couple of noises, and we will use these noises to drive a rotation on this vector over time. So as the point move, this vector will constantly rotate by a few degrees. We could use the point number and the frame to generate some random value, but for the organic look I want, a noise will work much better. So let's drop down a point bob, this time inside the solver, before the update position, and let's call it calc noises. We will create two noises, one for the direction vector and one for the up vector. So dive inside the point bob, and here let's start from the end. So let's take a couple of bind export. This will be noise dir, is a float parameter, duplicate it, and this will be noise up. So let's take turbulent noise, and we need two of those. This will be binded to the new attribute we will create. And to drive the noise, I don't want to use the point position this time. I want to use the frame, but I don't want to plug it directly to the position. First, I want to divide it for something. So we will have a further controller for it. We want to promote the second input. Let's call it divide by frame. And this will go in the position of both of the noises. On the noises, we will promote everything except the offset because we will randomize it by the point number. So let's take a random node and we will feed the point number inside the random. Let's take a multiply constant so we can change this value for the two noises. Let's set the first to some random number, something like this. Duplicate it and change the number, something like this. And let's take a set vector component. We want to set the y, so component 2. This will go into the value, and this will go into the offset. Let's duplicate it, plug the other multiply constant, and this will go on the other offset. And if we go on the geometry spreadsheet, they are not animated because we are multiplying by 0 for now. So let's change this divide by frame to 1 just to check if the noise are animated, and they are. Now, inside the point bob, let's promote everything else for the noises. So the type, the frequency, the amplitude, and everything else. Also for the second noise. And that should be everything for the point bob. So let's go back, and in here let's change the tweak the interface a little bit because it's getting a little bit crowded. So let's hide everything from here, and also where is it, this one, And let's see, this is the divide by frame. Let's take a couple of folder. Let's call it noise dir, and another one, not child of the other, noise up. So we take the parameter of the first noise and the second one here. So if we apply, I don't want it to be, let's set it to simple. So it's more organized. So apply, accept. And here let's set the noise to original Perlin. We want a zero center noise. So something like this, which goes positive and negative. Now, before shaping the noise, it will be nice to actually see some visual change. So let's make a room and create another point variable. This will be where we'll calculate the direction over time. So let's call it calc dir. And in here, we want to create a float channel to control the maximum angle that we want to rotate the points. So float max angle, CHF max angle, and create this parameter. For now, let's set it to something like 5. So now we want to use the output of the noise and fit it between this new max angle we created. So later on, we can use it to rotate the vector with two quaternions. So the first one will be angle up. So we want to fit the output of the point VOP. So it was F at noise up. And for now, let's fit it between negative 0.5 and 0.5. And we want to fit the result between the negative max angle and the positive max angle. And this value will really depend on how you shape the noise. You just need to make sure that you are not skipping too many values. So if you are clamping some values, it's not a big of a deal, but make sure to not skip too many values. So the source minimum and maximum should always be lower than the maximum output of the noise. Otherwise, you will end up with some weird rotation behavior. So let's create the other one, or rather just copy and paste this one. This will be the angle dir coming from the noise dir. And for this other stuff, it can be the same. Now we need a quaternion, as we did many times. So let's create a vector for. This will be quaternion up. And we want to use the quaternion function. And as usual, we want to use the variant where we define the angle and the axis of rotation. So the angle is angle up, and we need it in radians. So radians on angle up. And the axis, to rotate the up vector, we want to use the direction vector. So v at here. Why is complaining? Angle up is capital. And now the new up vector will be the qrotate function using the quad up quaternion we created, and we are rotating the old up vector. So now if we play it and maybe disable the position update for a second, you can see that the up vector is rotating super fast and in a weird way for now, but it's working. So before modifying also the direction vector, let's tweak the noise a little bit. We are working with the noise up, so we need to change this parameter. But first of all, if we change the divide by frame to some big value like 1000, you can see that this already is making a huge difference. And this is some value I want to keep, like 1000 for the divide by frame. It gives the look that I want. Now we can change the noise also, and maybe let's increase the amplitude a little bit and the frequency. Maybe decrease the roughness to 0.2. And of course, you need to wait the timeline to reset to actually see the change. And actually, I want to change the type to sparse convolution, which, like the original Perlin, is based on the 0, so we will end up with the correct values. And if I check here, I can see that I'm having a maximum output of, I would say, around 0.5, and same for the negatives. So this fit is actually good for the time being. And now let's also rotate the direction vector. And you can achieve a sort of similar effect even by just doing all of this only on the direction vector. But if we keep the up vector constant and the only one rotating is the direction, you can somehow perceive a sort of flatness on the all growing effect. This is why before rotating the direction vector, we are also rotating the up vector. So it will be a constant rotation and it will make the whole thing much more three-dimensional. So after the up rotation, let's create another quaternion. So vector 4, this will be quat dir, is equal to quaternion radians on the angle dir. And this time we want to rotate on the up vector, the new up vector. So now we can update the direction vector. So be at dir, it will be equal to the qrotate function on the quat dir, and the vector to update is also the direction vector. So now we have something like this, and we still need to shape the direction vector. So back on the point bob, let's set also this other one to sparse convolution, and I will set the frequency to 6 as this other one, and also lower the roughness. This time I will leave the amplitude to 1 to have some different values. So now we do have something like this. And we can also re-enable the position wrangle, so we have actually the point moving in space. They're so cute. Also, let me enable the real-time toggle, so this is the actual speed of the points. And as you can see, even if we set the initial vector to point all the same in the y, since we are rotating using a noise, and this noise, this rotation is accumulating over time, the points are actually losing the initial direction. This is something you might want, but I wanted to be able to control this thing. And in general, I want the point to actually be attracted to the initial vector a little bit each frame. So I have an initial direction and the point is wandering, but is always trying to get back to the original direction. To do that, we need to go back outside the solver, and where we initialize the attribute, we also want to bind the direction vector to a new attribute. Let's call it init dir. It will be equal to dir. And that's it. Now we need to go back inside the solver. And here, basically before the rotation of the direction vector, we want to do another operation. We want to take the direction vector, which still hasn't been rotated, and we also want to normalize it just to be sure. And here we want to do a lerp. We want to lerp between the current direction vector and the initial direction vector we just created outside. So we will lerp between the direction vector to the initial direction vector, and we will use a bias that we will create right away. So after the angle, let's create a float bias, CHF bias, and click here. As you can see, now they are totally wandering because the bias is set to 0. If we set the bias to 1, they will stick to the initial direction. But don't be fooled by this bias because we are inside the solver. You may think that if we want the points to follow, let's say 50-50 the trail, we just need to set it to 0.5, but this will make the point stick no matter what. Even a value of 0.1, I guess it will be too height because we are inside the solver. So basically this thing is accumulating over frames. So a good value for now and for the actual finish effect will be something like 0.01. So now you can see the points are actually wandering quite a bit, but they are trying to get back to the initial vector. And this is exactly the type of behavior I wanted for the entire effect. And on top of that, we also have the max angle. If we set it to something like 45, we do have some weird behavior, but this is basically telling of how many degree can I rotate each time I perform this operation. So 45 in this case is of course too much, but 5 will produce the kind of effect that I want. You can change it, of course, just don't go higher than, let's say, 20. 20 is already a little bit crazy for my taste, but could be interesting to see. I will set mine back to 5 and let's move on. And before moving on inside the solver, let's go back outside and fix the initial thing because I don't want a uniform direction. And also let's set the sphere now to something like 0.01. Don't set it to 0, otherwise it will mess up the initial vector because we will use the position. So give it at least some infinitesimal value to compute the vector. Now, where we define the initial attribute, we want to change this direction and up variable. We don't want it like this. So for the direction, we want to use the normalized positions. So normalize at p. And in this way, all the points, let me increase this scatter amount to 50 so we can see it better. We have the direction vector pointing outwards from the center of the effect. For the up vector, we actually want to compute basically another vector that, let me change the scale of the vector visualizers. I want to set this up vector for each point that points to another neighbor points. So we will have the two vectors perpendicular to each other. To do that, we want to use the near points function. We can't use the singular version because it will also consider the point itself. So we need the plural to get at least 2 points, and then we take the second point in the array. So let's create an integer array. We will call this pt, and we will use the near points function, geometry 0. We want to sample the position. We can set a maximum distance to 10, some might value, we don't care. And the maximum point, it will be 2, just the point itself and the point next to him. We can quickly visualize it by creating an array attribute. We will bind it to the pt array. And if we go in the geometry spreadsheet, we can see that each point has its own point number inside the array as first entry. We don't care about this. We want to take this other point, which is the point closest to it. So our new up vector will be the normalize function, and we want to basically subtract the current point position to its current neighbor. So we will take the point. From the input 0, we want to sample the position, and for the point number, we want to take the second point in the array we created. So pt index 1, and from this, we want to subtract the current position. So at p and close everything up. And why is complaining? Oh, I missed a parenthesis over here. So let's visualize the attribute 1 and 2. And you can see that we have the correct initial vectors. So if we zoom out and play the solver, we have something like this. Now, even if we can actually see the point moving, we really could use some visual feedback for the trailing effect. So just for the time being, because this won't be the final wrangle for the trail because it won't work for the connection, but it can give us some visual feedback for the time being. So let's take a point wrangle. We will call this create trail. And basically here we want to create a point each 5 frame. Then we can later on use to connect the whole curve. So if the current frame modulus 5 is equal to 1, so every 5 frame, then we will spawn a new point. So let's create an integer variable pt, and let's use the add point function, geometry 0 to the current position, semicolon, and close the condition. So now we should have some we can perceive some trailing happening. But as you can see, it's getting really, really slow. And the reason is because we are really spawning a lot of more points that we actually need. And the reason is because all the code we are writing inside the solver is running on all the points. So basically, after here we are spawning the new points, this code in the next frame is also running on the newly spawned points, so it's generating more points and so on. The way we can filter this is with a point group. So we want to go back outside here, and after the scatter, let's take a group node. We will call this moving. It's a point group, and we want to set it to all the initial points, so 50. So inside the solver, all the variables will be executed only on this group. So on the calc dir, run on the moving, and let's copy the name. So we can do it also on the update position, and more important, on the create trail. So now if we play it, you can see that it's much lighter and we actually have only the points we need. Even if this is wrong and we will fix it later, but now we can actually see what's happening within the points. So now that the overall movement is fine, the next thing we want to do is actually to split the points at a certain frame. And the idea is that the initial point outside the solver here, they will actually have some life attribute. Then inside the solver, we will compute an age attribute that will increment over time. So basically when the age will reach the life value, we will stop the point and we will spawn the branching points. So here where we define the initial attribute, let's also compute some float variable for the life. So float life, it will be equal a random number based on the point number. And we want to fit 01 this value. Where is the parenthesis? We know that the random will output from 0 to 1. So let's set two new float parameters. So min life and max life. What did I miss? The 1. Create this per parameter, and let's say the life will be from 3 to 5 seconds. We don't want the same life for all the points. And let's make some room here, and let's bind the life to an attribute. So f life is equal to life. And inside the solver, we should have the correct life attribute. So in the solver now, as the first thing after the prev frame node, we want to compute this age. And let's use another point variable. So right here, let's call it init age. And here we just want to say that the age attribute, so f at age, will be plus or equal the time increment of our scene. So time inc. And now if we create a visualizer for it, let's make it as a text. So age marker, we should have something growing with the time step. So as you can see, it's increasing. And also let's set this to run only on the moving group, because we don't need to compute the age for the still points. Now we want to go on the variable where we updating the direction over time. And here we want to state a new condition. So let's make it after the all rotation stuff. We want to say that if the age attribute is greater than the life one, then we want to reset the age. So age is equal to 0. And we want to set a new attribute. We will call this split, and it will be an integer one. So e at split is equal to 1. And let's close the parentheses. So now is not happening anything because we didn't define what to happen when the split will be 1. But if we check this new split attribute, So let's create a visualizer and disable this other one. Let's make it ramped from 0 to 1. As you can see, it activates when the age of the point will reach the life one. And right now it will stay that way because we didn't find anything else, but it's working. And I'm not sure if this age resetting stuff is still needed. Probably this is a leftover of my R&D stuff, but we will leave it as it is right now. We don't care about it. Now, since we know that we are about to generate more points, we want to make a little tweak on the update post wrangle, because here we are using the step value and the speed. The speed is basically randomized on the original point, but now that we are basically creating 2 points from one, we don't want the same speed to be inherited on the newly created points. So we want to compute another random value based on the point number that will update when we will generate other points. So after the multiplication here, we also want to multiply it for fit01 function with the random number generated on the ptnum. And as before, don't go from 0 to 1. Let's fit it from 0.5, 0 where I am, 0.5 to 1. So now the point that we will create, we will have another speed compared to the parent point. So we need a new wrangle. Let's take another point wrangle. We will call this split. And just for the sake of being silly, let me color this node. All right. Now, in the split wrangle, this of course will run also on the moving group. And now first we want to check if that split attribute has triggered to 1. So if the split value is equal to 1, then the first thing is we want to stop the current point from moving. To do that, just remove the current point number from the moving group. So set point group, geometry 0, the group is called moving, the current point number is ptnum, and we want to remove it from the group, so the value will be 0 and the mode will be set. If we close the if right now, we can see that we should already have the point stopping, because right now they are not anymore in the moving group. This is fine. Now where the point has stopped, we need to generate the branching. So let's go back inside the condition and make some room. We want 2 points for each parent. So it would be a good idea to use a for loop for just 2 iterations. So for int I is equal to 0, I less than 2, I plus plus to increment value. And now inside the for loop, let's see, we want to add a point. So int, we will call this pt branch, add the point, geometry 0, at the current position. And just as it is right now, let's make it run, and nothing is happening apparently, but in reality, here we now have 3 points. So we actually created the 2 points. We just need to compute a new angle and make the point inherit all the attribute we need from the parent. So let's see what we need to do to make this newly created point moving. First, we need to assign the new point to the moving group. That's also the reason because the trail is not moving, because when you create a new point, by default, it won't be added to any group, even if the point you are running the wrangle on are actually in the group. So let's do another set point group. Geometry 0, the group is always moving. The point number is not ptnum, of course, is pt branch. The value will be 1 because we want to add it to the moving group, and the mode will always be set. And don't test it as it is, but if you do, basically when the points will stop, everything will basically freeze. This is because we are not passing the life attribute, so the new point will have a life of 0. So each frame, the split attribute will trigger and they will spawn a new point. So let's fix it right away. So here, after the set point group, let's also transfer some attribute. So set point attribute. For the direction, we will change it later, but for now, let's take the original one. So 0, the attribute is direction. For the PT branch, the value is b at dir. We are taking from the parent for now, and the mode is set. Let's copy this line. We need a few more other. So we need to compute the life. So this time, let's change the name from the attribute, but don't take the original one. Let's compute a new one. We will create the variable right away. And after the life, let's also, actually, if we take the original speed, it will be the same no matter that we randomize it over here. So let's do one thing. Remove this last part from here. Here will be just the step multiplied by the original speed. And here, let's compute a new one. So plot speed, it will be equal to the fit we had in the other variable. So now it's actually different for the 2 points. And here is speed. It's complaining about the life. So let's also create the life variable, plot life. And let's, where we defined outside here, let's take it just as it is. So here, plot life, we can even still use the channel, but let's set it to the same value, so 3 to 5. And let's see what else. The up vector, we need it, of course. So let's copy this line. This is the up vector binding to the up attribute. And also the initial direction, of course. So it was init dir and the attribute init dir. And let's see if we play it, they stop. Here we need to bind the speed to the speed, not the direction. And also here randomize over the PT branch, or rather randomize it over I. So here and here. Now they should keep moving and splitting, and they does. And they do. The only thing, as you can see, they are, since they are inheriting the same direction vector, they will eventually branch, but not so much. For this, we also want to compute a small rotation when we actually spawn the point. So basically, the idea is that when we spawn the 2 points, before inheriting the whole direction stuff, we want to rotate the 2 points for an angle, one in the positive value and one in the negative, let's say of a 45-degree angle. So after the life, let's compute a new float variable. We'll call this angle, and it will be, we said 45, and we want the negative for the second iteration of the for loop, so we can multiply it by I minus 0.5, everything between parentheses, multiplied by 2, and also a couple of parentheses here. So basically now the first iteration of the for loop will have 45, the second will have negative 45. And now we need a quaternion, of course, so vector for, we can call this quat dir, quaternion in radians. We want to plug the angle for the angle, and we want to rotate the direction on the current up vector, so b at up. And after this, vector dir will be the qrotate function using this new quaternion, and we want to update the current direction vector. Is quote dir, and here we need to pass the new direction variable, not the attribute directly. So just erase the v and the at sign. So now when they split, they don't follow the original direction right away, but they do this angle rotation, and then they keep going with the other behavior for the rotation. So maybe let's decrease the point back to make at least 2, otherwise the up vector here will not be computed correctly. So we can at least see better the behavior of the points. And I don't really love this. There's too much twirling around, so maybe we can decrease the amplitude of the noise a little bit. So let's try 0.6 for both. We still have some, but I'm good with it for now. So what next? What next? Let's start to think on how we can connect this point to create an actual set of lines. We want to do it with an add node, so outside the solver. What is this? Add node. And we don't want to connect all the points. We want to connect it by an attribute, which we don't have yet, but we will compute a name attribute to correctly connect all the points based on the curve. So here, outside the solver in the init attribute, let's also compute a name. Let's create a string variable. So string name, it will be equal to I to A, the PT num. So we can append it to an attribute. So after here, let's create a string attribute. We will call it name, and it will be equal to curve with underscore plus the name number, so to speak, we just created. So basically now all the starting points will have this name with the number of the point appended. The problem is this needs to be calculated differently for each splitting that we have. So we need to go back inside the solver. And here, where we're splitting the points, we also want to compute a new name. So let's make some room. Let's create a string variable, string name. It will be equal to the parent name, and we will add to that parent name another underscore, and plus the I to a function of this ptnum plus I. So we have a different one based on the iteration of the loop. So now we should have right now 1, 2, 3, 4, a few different names. And we don't, because we do have to bind it to the attributes. So let's copy one of these. Let's take the up one. So here we want to set the name to the new name we defined. And now we should have some different names. What's happening? Let me reset the simulation. Let's see. Yeah, we do have some names. We're not transferring also to the trail for now. So these are all points for the trail. They don't have the name. And as you can see, these are some weird names. They are consistent in the term that they are unique for each curve. So that's enough for us for the add node. But as you can see, they are not really ordered in some meaningful way. But if we do it right here now, we can, where is it? By group, by attribute, we want to use the name attribute. And as I said before, the trail is not correct. So this is the reason why we are having this mess right now, but we will fix it right away. So back inside the solver, let's go on the variable where we are creating the trail. And for the time being, let's just try to transfer the name attribute and see what happens. So set point attrib. We want geometry 0, the attribute is name, the point is pt. the value is as at name, and the mode is set. So if we let it run and let's see the ad, as you can see, is partially fixed because we are actually transferring the name, the correct name on the trail point. But this is why I said at the beginning of the video that this type of trail won't work. This is because the point order. If we visualize it, and let's take this curve, for example. As you can see, the point order is growing. It doesn't matter that it's keeping some value because we are connecting by name. So the only thing that matters is the order. But the problem is that the first point is the one is moving. So it will always be at the start of the curve, and this will create this problem in the connecting the points. So how do we fix this? Basically, when we are creating the point for the trail, we don't want to spawn a point that acts as the trail, but we want to stop the moving point, create a new point, and the new point will be the one that is moving. So basically, we will keep a constant growing order in the points. And to do it, let's just use the setPointGroup function. So geometry 0, group moving. We want to push this point to the moving group. So pt one set, and let's copy and paste it. And we want to remove the original point from the moving group. So at ptnum, and this will be 0. Now the only thing is we need to also promote all the attributes, the direction, the up to the new pt. Otherwise, this new point will be part of the moving group, but it won't have any attribute to know where to move. So after the name, let's also set all the attributes. So let's see, let's copy the line for the name, and we need to promote the direction. And this time will be every time just passing the original attribute. So directly be at dir, also the initial dir, so init dir, and this will be at init dir. We also need the up vector, so up be at up. And let's see, we also need the age and the life, so another two line, age, life, and these are two floats, so f at age, f at life. We need to copy the split attribute, otherwise we will never have a new split. So this was an integer, at split. And I believe that's it for now. Let's see if it does work. It doesn't work. Let's see. Yeah, we forgot to promote the speed. So speed, another line. This was a float value, so f at speed. Okay, now it's working again, and hopefully if we go on the add node, we don't have that problem anymore. We do have some minor issue. We will fix this too right away, but as you can see now, the points are connecting in the correct way. So why there is this gap between the lines? Actually, for two reasons. The first one is that when a point will split, it's not mandatory that we'll actually create a trail at that frame. So we will miss a piece from that. And the other one is that we are not creating a first point for the branching. So basically, we will miss a point on this line and 1 point on the branching lines. So go back inside the solver. So to fix the first half of the problem, we need to add a condition here on the create trail. And we just need to say that this trailing will not happen only when the frame will be divided by 5, but also when also when the split attribute will be equal to 1. So if we do this, we should still have the gap, but it should be smaller. And as you can see, we actually have a new segment which is shorter than the other one, meaning the Here we have the modulus of 5 for the frame, which is 1, and here the point had the split attribute 1, so we are creating another point on the trail. Now, to fix the other half of the problem, we need to act here, where we are doing the splitting. And here what we want to do is basically we want to create another point that will act as the root of the branch. So after we declare the name, let's make some room and let's create another point. We will call this one pt root. Always the add point function, geometry 0, add the position as usual. Now, by default, this point won't be added to the moving group, and this is fine because we don't want it to move. This means we don't even have to set all these attributes, but we need to set at least the name for the connection part. So let's add a new line, and we want to add the name to the pt root this time. And let's give it a try. And we fixed also the other problem. And basically this is it for the main movement of the effect. And now we need to compute some more stuff that we will need for the thickness part. So if you're just interested in growing lines without everything else, you can stop here if you want. Maybe just set the points to 50 for a second just to test it. Like this, and as you can see, it's also super light to compute. And we have all the control we want to shape it. We need the noise and the angle. Now, for the thickness, let me decrease this back to 2. I want to combine two factors. I want the line to be thinner towards 0 as they grow, so controlling the animation. And also I want to consider some sort of U value of the individual segment, meaning I want the line to be thinner at the center and thicker at the joint of the curve. Now, to compute the main thickness, first we need some birth attributes, so we can remap the birth frame relatively to some sort of offset, which will be the length of the growing effect. So for the starting point, let's just initialize it here. Let's create an integer attribute here, birth, and this will be equal to 0 because these are the initial point. Then we need to go back inside the solver, and here we need to compute the birth when we create the new points, basically. So on the split here, where after the name, let's create an integer variable called birth, and it will be equal at the frame casted as an integer, so we don't have the annoying green thing over here. And we need to set it as an attribute also, so let's copy the name and let's paste it. This one is birth, and we need the birth variable we created, so birth. And we need this also on the pt root. So this will go pt root. Now on the create trail, similarly to before, we need the birth frame, so let's copy this line, int birth, and let's paste it here. And we want to set it also on the trail pt, so this birth and birth. So let's run it and see on the geometry spreadsheet, we do have the correct birth frame. So now outside the solver, we can use this value to create some thickness. So let's take another point wrangle. And for now, let's create a float thickness attribute that will be equal to the fit function. And what we want to fit is the current frame number. And we want to fit it from the raw birth value to the birth value plus some offset. If we say birth plus 100, basically the time will take the thickness to grow will be 100 frame. And this will be fitted between 0 and 1. So now if we create a visualizer, where is the tick? As you can see, we have something like this that we can use to drive an actual thickness on a polywire node. So let's clean some stuff here because we basically done, so we can go down with the stream. And here, let's delete every attribute except the thickness. At least in my case, I don't need anything else. Then I want to take a fuse node so we can connect the intersection point. Then we can take a resample to smooth this whole thing up. We can set it to, let's say 0.1 is fine, but we want to output it as a subdivision curve. And finally, let's take a polywire. So this will be, let's say, 8 division, and we want to use the thickness we created to drive the thickness. So thick. And here, of course, you can use this other parameter to control as a global multiplier, or we can also create it here. So let's say by chf amp, create this per parameter. As you can see, as usual, is the same thing. So let's say I want to set this value to a lower one, so 0.04. I want to control it with this one, which is better. And now we need to add on this, on top of this, the the thickness of the individual segment. To do that, we need to do another little wrangle inside the solver itself. So let's go back inside the solver. And here, let's say before the splitting, let's take another point wrangle. We will call this calc u. And in here, we want to retrieve the age and the life of the point. So float age is equal f at age, float life is equal f at life. And then we want to compute a u variable. So float u, it will be equal to a fit result, and we want to fit the age between 0 and the life, and going from 0 to 1. We also want to remap all of this, otherwise it won't make sense. So chramp, uramp, and another parenthesis here. Let's bind it to an attribute, so f at u is equal to u, and create this pair parameter here. Now let's spin this thing for a moment, and let's go outside after the add, so we can check this new u value. And we don't need to transfer the u over the points, because right here we are calculating the u on all the points, not only the moving one. So here, as you can see, we have from 0 to 1, because we have a linear ramp. So we want to set it to be spline and do something like this. As you can see, is higher in the, or rather lower in the middle and higher at the intersection. So here, where we are calculating the thickness, so let's rename it to calc thickness and unpin this window. Here, let's retrieve the u, so f at u is, or rather the opposite, float u is equal to f at u. And here, let's just multiply it within everything else. So go back on the polywire. As you can see, we also have the, we need to recalculate the solver. Yeah, we also have the variation over the single segment. Let's set it back to 50 point to see what do we have at the moment. If you see is slower compared to before, this is because of the polywire and the resample node, until the add node is really, really fast to compute. And maybe I want to increase the noise back, because right now there's not much of a movement. So let's set it back to 1 and 1. Yeah, now it's better. And this is pretty much it for this tutorial. We done everything, and all I did is just to use the global thickness value to drive some color into the rendering, but there's really not much going on. So, as usual, I hope you enjoyed this content, and if you did, subscribe to the channel, drop a like, whatever, and I hope to see you in the next one. Cheers!